So, today we go a little further with our discussion of how to actually do mode locking. So far we have studied the theory. Today we are going to talk about at least one case in which mode locking is done and how it is done. If you read any standard textbook, at this stage what people discuss is active mode locking, passive mode locking and acousto-optic modulators. We will take a rain check on that, we will not do it right now, because our primary goal is to understand how a tie-sapphire laser works at this point of time. So, we will skip that for a moment, we will come back and do it in the module after next, after we have shown you tie-sapphire laser. But today we want to learn about a very strange way in which mode locking gets done and femtosecond pulses are produced in titanium sapphire laser. And the way it is done is called Kerr lens mode locking. And in fact, Kerr lens mode locking happens in a manner in which you do not even perhaps understand that it is happening. So, it is almost like it happens by itself. So, the question is, what is this magic, what is the mystery by which this femtosecond pulses that we are looking for so desperately get produced by themselves without us having to do much? And is there anything that we can do to improve the situation? That is what we will discuss in this module. In the next module, we will go and talk about an actual tie-sapphire laser. But before that, let us quickly recapitulate what we have discussed in the last couple of modules. We have talked about longitudinal modes in detail. So, now I hope we all understand that a laser can have many modes. Many modes mean many frequencies that can be sustained in the cavity, and the kind of cavities we have and the kind of color of light that we deal with, we always deal with things like 10 to the power 6th, 10 to the power 6th mode, 10 to the power 6 plus 1th mode and so on and so forth. So, these modes are only slightly different from each other as far as frequency or wavelength is concerned. So, and we have also said that this spectral width of each mode is something that we have also calculated, and given the modal wavelength and given the width of the spectrum, we know what the total number of modes is. Okay. And then we introduced another term which is very important as far as discussion of laser is concerned, not just ultrafast lasers, any kind of laser, that is quality factor. Quality factor is essentially a weighted ratio of energy gained in the system and energy lost during one cycle. Energy gained in the system means what is the build up, how much of population inversion you achieve, and that is usually achieved by pumping it with an intense laser. And energy lost can be not just by emission of light, but also due to things like heat and so on and so forth. And then without derivation, we have given you the relationship between the spectral width of each mode and the quality factor Q. Very soon we will come to a discussion of what is called Q switching, where we can generate pulses, not very short pulses, but pulses nevertheless, by switching the quality within the cavity. And then this is a figure that we have shown maybe 3-4 times already. What happens when you have many modes? First of all, when they have no phase correlation. Secondly, when they do have phase correlation. And what we have said is that when the phase relationship is a function of time, then you get a random fluctuation and essentially you get a CW output. However, when you have a phase relationship which is independent of time, then you achieve what is called mode locking, and that is when you generate pulses. And while talking about pulses, we also said that you get the intensity by taking square of the field. So, when you combine n number of pulses, this is something I do not think I said earlier. When we combine n number of pulses, essentially the intensity at the peak turns out to be n square multiplied by E0 square, where E0 square is the maximum amplitude of field associated with the normal modes. So, you see you couple 5 modes, let us say E0 is same, you couple 5 modes, you will get 25 multiplied by E0 square. You couple 500, that will be 500 square multiplied by the same E0 square. So, that is how peak intensity grows very significantly as you increase the number of nodes, number of modes that are coupled. And we said that this is the shape of the intensity of each pulse. If you zoom into it, you have one major pulse and you have very short side bands, and the widths are very, very small here. We also talked about tapetation rate. Tapetation rate turns out to be 12 by C, which is essentially round trip time within the cavity of length L. Pulse width, however, turns out to be something that is dependent not only on the length of cavity, but also on the number of modes that are coupled together. And since we know the relationship between number of modes and lambda 0, the modal wavelength and delta lambda, we worked out this relationship that pulse duration, Tp is not really full width at half maximum. Pulse duration turns out to be lambda 0 square divided by 2c delta lambda. And this is something that I have not shown earlier. This is, so you can see when this was published, 1964, in the very beginning of the invention of lasers itself. So, this is what you get, this is what I was talking about. You couple 5 modes, these are the kind of pulses you get, quite broad and less intense. You couple 50 modes, you get sharp and intense pulses, right. So, this is the essence of mode locking and production of pulses. Then we said that the best case scenario you can get is when you have transform limited pulses. So, product of the pulse width, full width of half maximum, and product of full width of half maximum of the spectrum turns out to be a constant, which is 0.441 for Gaussian pulses and different numbers for pulses of different shapes. But remember, this is the best case scenario you can get. Just because you have a certain bandwidth need not necessarily mean that you have a pulse width that is as small as you really want it to be. You really have to have good alignment in order to achieve transform limited pulses. Okay. Before we move on, it is time to talk formally once about transverse modes. What is a transverse mode? You take a laser beam and put it on a surface, okay? Maybe expand it and put it on a surface. You are going to see a spot. The question is, what does this spot look like? Okay. If the spot looks like a circle, roughly a circle, without any dark spot anywhere, it is a patch of light, circular patch of light, then this mode is called TEM00 mode. TEM means transverse electromagnetic mode. T for transverse, E for electromagnetic, M for mode. TEM00. 00 means there is no node in any direction. This one is called TEM10 mode. That means there is one node in a particular direction. This is 1-1 mode. One node along this direction, one node along this direction. Okay. Now, the problem is this here is 1-0 mode. This one also has one node. This is called 0-1 mode. Which one is 1-0, which one is 0-1? There is no good answer to that, because directions are all arbitrary, right. You might say that this surface is xy. So, this is x axis. So, if there is a node along this, I will call it 1-0. If there is a node along this direction, I will call it 0-1. But then x and y, these are all relative, right. It depends on how you define the directions. So, as E.W. Small says in this chapter of J.R. Lakovich's Topics in Fluorescence Spectroscopy. This is not the Introduction to Fluorescence Spectroscopy book. Lakovich also has several volumes of Topics in Fluorescence Spectroscopy published long ago. There in this chapter 2, E.W. Small says one man's 1-0 mode is another man's 0-1 mode. So, it depends. You look at different books. The crux of the matter is this number 1 or 2 or whatever it is tells you how many nodes there are in a particular direction. Now, which direction comes first, which direction comes second is absolutely a matter of convention. Okay. This one is 4-0, or you might want to say 0-4 mode. Before coming to this one, do these modes remind you of something that you have studied in first year BSc or something? Yes, they remind us of orbitals, right. The shapes are very much like orbitals. In fact, when I taught this course actually in a classroom, one of the students sent me these pictures of orbitals and said, don't they look very similar? Actually, yes, they do. Okay. Now, the last, so you can go on and on. These modes, what about this? Is there a node here? You have what looks like a 0,0 mode, but then there is a hole punched in it. This is called in colloquial terms a donut mode, 1,0 star. Now, one thing I have not drawn here is you can also have nodes that are radial, right. So, here I have drawn nodes as planes, but you can also have a spot, then a circle of darkness and then another spot of light, or you can have 2 of them, 3 of them, 4 of them. So, radial nodes are also there, again you call them 1,0, 2,0, so on and so forth. Now, this donut mode 1,0 star is of particular importance in things like super resolution microscopy. So, I do not think we will have scope to discuss super resolution microscopy in this course, maybe sometime later. So, I think we know, right, what is the smallest spot that I can get by focusing light of wavelength lambda, lambda by 2, right. Why is that so? It is called the refraction limited spot. So, you cannot make it any tighter. You can think that we will do tight focusing and the spot will become smaller, 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 but then it cannot become 0. There will always be a finite size, because below that diffraction will set in and broaden the spot a little bit. So, diffraction limited spot. So, if I use what kind of I want to do, say, visible microscopy, visible light microscopy, 600 nanometer, 500 nanometer, something like that. Let us say I am using a 500 nanometer laser to do microscopy. So, then the best resolution I can get is 250 nanometer, right. So, you cannot do any better by usual microscopic techniques. As you know, I think 2014 Nobel Prize was for super resolution microscopy. Who are the people who got it? Stefan Hell was one, Betzig was another one, and Morner was a third. Morner actually got it not for super resolution microscopy, but for single molecule microscopy and spectroscopy. Betzig and Stefan Hell got Nobel Prize for super resolution microscopy. Super resolution microscopy means doing microscopy using visible light with a resolution that is better than diffraction limit. How do you do it? There are well, Stefan Hell's method is you take 2 pulses, one with a TEM00 mode, another one with 1,0 star mode, and you overlay them. And then you can play around with this and have destructive interference between the 2 pulses. At the instance when you have destructive interference, what happens is this, wherever there is light in this 1,0 star mode, in the composite beam, in the composite spot, that becomes dark. So, the beam becomes smaller, smaller in radius. Okay. So, of course, when I say radius, what do I mean by radius? We will come to that. So, 1,0 star, do not think it is just for our purpose. When we do ultrafast spectroscopy in bulk mode, we do not want 1,0 star mode. We will see why, but it is useful in super resolution microscopy. But for now, let us only focus on this TEM00 mode. In TEM00 mode, if I want to plot intensity, this is what it looks like. So, intensity is maximal at the center and it falls off on the 2 sides. So, in the best case scenario, you have a Gaussian kind of distribution. My diagram does not look Gaussian, that is due to my inability to draw very nicely. But in TEM00 mode, you do have Gaussian distribution of intensity spatially. And now, when I say Gaussian, is it 2 dimensional or is it 3 dimensional? Yeah, there are 2 axes, right? When you take a spot, you have one axis and you have another axis here. So, it is Gaussian with respect to this, Gaussian with respect to this also. So, you start at the center, intensity falls off as you go out radially. Okay. So, this is your TEM 00 mode, and you will see why we are suddenly discussing these. They are actually useful in Kerr lens modelocking. Now, let us talk a little bit about Kerr effect. Kerr effect says that if you have an intense beam, then it can modulate the intensity of the medium on which it is incident. And without going into further, this is a nonlinear optical phenomenon. We are going to talk about nonlinear optics a little bit later on, but today let us just take it axiomatically. The refractive index of the medium on which an intense beam falls changes in this way. N0 is the refractive index when an intense beam is not impinging on it. When it falls, then there is a second term which depends on the intensity of the beam, N2 into I. Now, one thing one needs to be careful about is N2 is not, what is the unit of refractive index? Refractive index? No unit, right? It is a ratio. But do not think that this N2, just because I have written it N2, do not think it is devoid of unit. Because see, the equation has to be dimensionally consistent, right? And here it is not just N2, N2 multiplied by intensity, intensity does have a unit. So, N2 has the dimensions of inverse of intensity. Okay. Now, see what happens. You have this Gaussian beam. I hope we all understand contours, right? As the contours get smaller, that it represents the we are going to the peak, higher intensity. So, as this is the center of the beam, as you go out, what will happen? Intensity will fall off in this manner, as we have discussed, right? And this, since this is from a printed book, this is a prettier diagram than I could have drawn. What will happen to the refractive index? Intensity is maximum at the center, right? And it falls off on the two sides. So, what will happen is, for a sufficiently intense beam, the refractive index will also fall off in the same manner. Refractive index will not be the same across the beam profile in the medium. Are we clear? Is there a question? So, you are going to have this kind of a Gaussian variation of refractive index in that medium. This is called Kerr lensing. Why is it called Kerr lensing? Because think of a lens, think of a convex lens. How does it work? For a convex lens, the any light impinging on it goes through more of the medium, right? So, more refraction takes place. Here we do not have convex or concave medium, we have, let us say, a cubical block, but we, due to intensity of the beam, we are bringing in a gradient of refractive index. So, effectively this block, which had no reason to act as a lens, is now going to act as a lens. Are we clear about that? In this region, refractive index is less. In this region, refractive index is more. So, what happens? Okay, let me put it in another way. What happens when a parallel, when a collinear beam of light goes through? Here, it goes through a region of smaller refractive index, or rather smaller change in refractive index from what it actually is. So, it will more or less go straight. As you go inside, what will happen? It will bend more because refractive index is more. So, eventually what will happen is, this beam that was going straight will get focused. Are we clear? What kind of a beam will get focused? An intense beam only. This is the tricky or important part here. If you take torchlight, make a collimated beam out of it and make it fall on a medium, you will not see Kerr lensing because it is not intense. If you take the output of say helium neon laser, put it on a medium, you will not see Kerr lensing because it is not intense. You take a continuous wave tie sapphire laser, make it incident on this some medium, you will not see Kerr lensing. You take the same tie sapphire laser, but in pulsed mode, you are going to see Kerr lensing, because remember what intensity is, it is n square multiplied by E0 square, right. More the number of modes, better it is. Okay. So, mode locked laser, mode locked light is what is going to produce this Kerr lensing effect. Okay. So, an intense beam will get focused and a weak beam will not get focused, because do not forget the beam itself is bringing in Kerr lensing. Okay. This is the part that we really need to understand. It may not be so easy to follow when you hear it for the first time, and then it is going to get more interesting as we go further. So, what we have said is pulse light gives you intense beam. So, in a mixture of pulse light and continuous wave light, what will happen? You have a medium through which your pulse light and mixture of pulse light and continuous wave light of the same wavelength range is going through. The pulse light will get focused and the CW part will not get focused, right. So, if we show it diagrammatically, but before that this is just for the record, again since we are not deriving, it is not much of a fun, but then just for the record, the focal length of a Kerr lens is given by W0 square, where W0 is the beam waist. Beam waist once again is full width of maximum of a Gaussian beam by 4n2 I0 multiplied by L, where L is the thickness of the medium, length of the medium. So, now with this understanding, we suddenly have something called Kerr lens mode locking. What is that about? Let us see. What did we say? We said that your induced refractive index depends on the intensity. So, we are starting with this, that we have a mixture of CW and pulsed light. Okay, in a laser somehow, so we can think like this, you have started a laser and some of the pulses have got mode locked, maybe 5 pulses, and there are other pulses that are not mode locked. This mode locked pulsed light is going to be intense, so it will get focused. Okay. Now, think that we have a laser consisting of your tie sapphire crystal, nothing else, titanium sapphire crystal and 2 lenses. We will introduce something very shortly. That tie sapphire crystal itself can act as a Kerr medium, is not it? Light is going through it, it is a solid crystal. So, any light that is passing through the tie sapphire crystal itself is going to show this Kerr lensing effect. Okay. So, this is what will happen. You have a mixture of CW and in fact, it is not a simple mixture of CW and pulse, maybe there is a gradation. So, intense light will get focused like this and CW light, which is not so intense, will not get focused or will get focused to a lesser extent. Okay. So, the dotted lines denote the CW light, the solid lines denote the intense light. Is there any reason why the solid lines are inside and the dotted lines are outside? Do not forget that it is a Gaussian beam. So, intensity is actually maximum at the center. Okay. So, it is a sort of a synergistic effect. So, you are going to have this kind of a Kerr medium, your pulse light will get focused, CW will not get focused. Now, if we introduce an aperture here, what will happen? See this one near M2, here these black lines denote the section of an aperture, pinhole. The CW light in the fringe will get blocked and pulse light more towards the center will pass through. Okay. So, a combination of Kerr medium, 2 mirrors and a pinhole can give you a laser whose output is pulsed. Any question? So, what I am saying is this, you understood that this titanium sapphire laser, titanium sapphire crystal, that itself can act as a Kerr medium, right. You are pumping it and then you have this light passing through it, the stimulated emission. To start with, let us say some modes are locked somehow, that will happen, right. There is always a possibility of happening. So, that mode locked beam of light is going to get focused, and unmode locked CW light will not get focused. Now, if you introduce an aperture here, then the CW light which is on the outer side, that is going to get cut, and the intense mode locked light which is at the center will not get cut. So, it will go through. So, only the pulsed operation will be sustained, CW operation will not be sustained. Okay. Now, let me say something more. Is that aperture even required? To understand, to start with, it is good to have the aperture there. Suppose I do not have an aperture, will this thing still happen? So, you have curved mirrors, right. So, something that is focused and something that is not. You make the cavity in such a way that you have curved mirrors which support this kind of focusing here. So, anything that goes straight will not come back here. So, it will automatically go out of the cavity. Remember, the terminal mirrors are never plane mirrors, they are always curved mirrors. So, in fact, that aperture is not even required. You can get pulsed operation without the aperture also. Okay. So, this is called Kerr lens mode locking. Okay. Now, Kerr lensing gives you pulsed operation, that is great, but it always makes things a little, it also makes things a little difficult for you, because it introduces what is called chirp. What is the meaning of chirp? Before that, let me say that these are nicely animated slides that you are going to see. I did not make them. These were made by Dr. Johur Alam Mandal of BRC many years ago. She was kind enough to give me the slides, so I used them. So, the thing is this, in Kerr lensing, you have this pulse light incident on it. I hope it is not very difficult to recognize this as a pulse. I am drawing the electric field, not the intensity. Then it induces Kerr lensing. Okay. So, effectively, even though it is not, even though it is just a slab, as far as the light is concerned, the slab behaves like a convex mirror like this. Okay. What you see here is sort of a heat map for your refractive index, becomes a convex mirror, and then focusing takes place. All that is good, but the problem is, what is the meaning of drawing a pulse like this? It is a mixture of many modes, is not it? And more modes you have, the better it is. So, you have different frequencies and you have a lens. What is a common problem that is encountered when you have polychromatic light being focused by a lens? In secondary level optics, different colors, that is a hint. The problem, yes, what different? The speed is different, exactly. So, what happens? And what is that called? It is called chromatic aberration, and you correct it by using achromatic doublets, right. So, that sort of negates the chromatic aberration. So, here, since there are so many different wavelengths involved, do not you think chromatic aberration will happen? Yeah. So, and as a result of chromatic aberration, what you will get is you will get a chirped pulse. Some color will go ahead, some color will go behind, and that will cause a broadening of pulse. So, before you can actually start making a laser, one needs to correct for this chromatic aberration. Okay. One has to correct for chirping. How? We will do that in the next module.